Good day, everybody. This is going to be the Rotational Motion Practice Problems podcast. And before we get started, I want you to remember what a lot of the letters that we used for these formulas are, because we're going to be using a lot of Greek in this rotational chapter. And so let's begin with the first one. If you remember, we had D for distance, and my pen's not working. There we go. Let's try this again. We had D for distance, and that's going to be measured in meters. But if you want to find the linear distance, you can take the Greek letter for distance, which is going to be theta, that's measured in radians, and simply multiply it by r. So if you want to find the linear distance, you take the Greek distance and make it Greek-er. Now, you can also do the same thing with linear velocity. So if I want to find the meters per second for v, you can take the Greek letter for velocity, or what we call angular velocity. We use the small Greek letter omega for that. Looks like a cursive W. And we multiply that by r. So you make it Greek-er. And if you're found the rotational velocity and you multiply by r, you get the linear velocity. And then finally, we can do the same thing with acceleration. If I want to find linear acceleration, in other words, meters per second squared, you take the Greek letter for acceleration, which is going to be alpha. Some of you call it Jesus fish. And so that'll be radians per second squared. You multiply that by r, and you're going to get the linear acceleration. So let's do a few of these so we know what's going on. Number one, it says a merry-go-round has a radius of 3.5 meters. We're going to use this for most of the problems, so keep that in mind. How far, so I want to know the linear distance, did the person go who spun 180 degrees? But actually, I don't want to know linear distance. I want to know it in radians. Well, in this case, it's just going to simply be a problem where you do a conversion problem. So I'm going to take 180 degrees and just simply set it up like the old-fashioned conversion problems we did. I'm going to put degrees on the bottom because I'm trying to get that canceled out. And there are 360 degrees in one circle, and there's 2 pi radians in one circle. And so therefore the degrees are going to end up canceling out here. And 2 divided by 360, they're going to sort of reduce down to 1 over 180. And so I end up having pi radians. Or I really want you to use significant figures here, so I want you to make it a number. So you're going to actually put this as 3.14 radians. In part B now, it says, how far did the person go in meters? Well, I want you to look at this formula that you just wrote up here. In meters, it'd be English D, or the regular letter D. But in order to figure out the regular D, I'm going to take the Greek letter theta and multiply it by r. Well, you just found theta, which is the number of radians up here. So I'm going to take the 3.14, multiply that by my radius, which is, where was it? 3.5. Come on, pen. And so that's, the radius would be meters per radius. A radius is the same thing as a radian. And so the radians are going to end up canceling out. And I'm going to end up getting 10.99 meters. And so that gave me my linear distance after knowing my radians. Now, the next one says, what's the angular velocity? Well, angular means use the Greek letters. So I'm going to come up here and I'm looking for angular velocity. So angular velocity, if it rotates 0.25 revolutions per second. Well, angular velocity is not going to be in revolutions per second. It's going to be in radians per second. So once again, I'm just going to simply make this a conversion factor. We get my revolutions to cancel out by putting 1 revolution on the bottom. 1 revolution, there are 2 pi radians. Remember, 2 pi r is the circumference of a circle. And so therefore, an r is a radius, and a radian is the same thing as a radius. So I'm just going to multiply by 2 pi. And this ends up being 1.57, or half of a pi, radians per second. So if you remember in the last chapters, we measured velocity in meters per second. Well, the Greek is always measured in radians or radians per second. So up here we found theta, and it was measured in radians. But then you switch it to linear distance and you measure it in meters. Well, that brings us to part D. It says, what's the linear velocity? So I'm going to know meters per second now. Well, if you want to find linear velocity, look at this formula right up here. You can simply take the Greek velocity, or the angular velocity, and multiply it by r, or make it Greek-er. So I'm going to take that 1.57, and that's radians per second. Divide that, or multiply that by the radius of 3.5, and that's meters per radian. And so therefore the radiuses cancel out, and I'm left now with 5.5 meters per second. Part E, I'm just going to go right down through the same thing we learned all year. We started with distance and went to velocity. Now we're going to do acceleration. It says if a ride started at rest and reaches a maximum speed of 3.75, well, if it started from rest, that's my zero. It's going to be my beginning velocity. And I'm not going to put a V here. I should put a omega, because that's my radians per second would be my angular velocity. And it does that in 6 seconds. Well, that's time. What's the angular acceleration? Well, if you remember, the old formula for acceleration was change in velocity over change in time. Well, now you simply change it using the Greek letters. So instead of an A, I'm going to use an alpha. Instead of a V, I'm going to use an omega. And so watch how easy this is. If the car started at 0 and went to 3.75 radians per second, so it's final minus initial. And this is once again radians per second. The time it did this in was 6 seconds. Get rid of that. And so if you divide that 3.75 by 6, you end up getting 0.625. It's going to be radians per second squared. So just like we used to do acceleration in meters per second squared, this is going to be radians per second squared. Part F says, well, what's the linear acceleration if it did that same thing? Well, once again, you simply take the Greek and make it Greeker, and that gives you the regular acceleration or the linear acceleration. So I'm going to take alpha and multiply it by r. So that's at 0.625 radians per second. Multiply that by the radius, which was 3.5 meters per radian. Because a radian's the same thing as a radius, or same length is anyway. And when you put those two things together, you end up getting 2.18. Now it's meters per second squared because the radians canceled out. And this should have been radians per second squared. Lastly but not leastly, it asks for the frequency. Well, the frequency is how many times does it go around, or revolutions per second. And in this case, the frequency says it rotates 3.55 times, or revolutions, in 4 seconds. Simply divide those two numbers and you end up getting 0.88 revolutions per second. And a revolution per second, or a cycle per second, is also called a hertz. It's also called a HZ, which is called a hertz. Lastly but not leastly, we have what is the speed of the ride if it rotates 3.55 times in 4 seconds. So I'm sorry, not the speed, what's the period of the ride? Well, the period is the amount of time, just like when we looked at Kepler's laws, it was the amount of years it took to go around the sun. Well, instead of revolutions per second, what you can do here is take the inverse of the frequency. Watch what happens here. I'm simply going to flip that upside down. So instead of taking 0.88, I'm going to say 1 over 0.88. I'm going to show you a different way you can do this too. And that ends up giving you 1.13 seconds per revolution. Now, another way you can do it is simply flip-flop these numbers up here. Since time or period is the inverse of frequency, I could take 4, divide it by 3.55. 4 is seconds. 3.55 is revolutions. And that's going to end up giving me 1.13 seconds per revolution. And so that should be the whole worksheet there. And I hope you enjoyed the show. Bye.